Hello all, welcome to my channel PSA Tech Classroom. Uh, in today's video lecture, I would like to tell you the example problem of the Butterworth filter. So far we have covered four problems. In that, one problem is finding the order of the filter, and second problem is finding the poles of the filter, and in the third problem finding the transfer function of the filter, and this is the example problem 4. So far in the previous problems we checked the given data, either in the alpha s and alpha p, omega s and omega p. They have given direct data, so we have substituted those data in the given formulas for finding the order and the poles. That is okay. Next, now in this type of problem, see here, they didn't give you any of the values directly. Problems you may get in the examinations. From this problem you have to extract the omega s and omega p values, and alpha s and alpha p value. So this is an important problem you may get. There are high chances of getting such problems in the examinations. So let me read the problem first. For the given specifications, design the analog Butterworth filter, which is in lying whose transfer function h of j omega is lying between 0.9 to 1 for the range of 0 to 0.2 pi. The omega frequency, omega is the angular frequency which is lying between 0 to 0.2 pi, and h of j omega is less than or equal to 0.2 for 0.4 pi less than or equal to omega less than or equal to pi. So this is the question. It means that he is explaining that h of j omega is the transfer function of the filter. Okay, the transfer function is lying between 0.9 and 1 when the angular frequency is from 0 to 0.2 pi. The same transfer function h of j omega is less than or equal to 0.2 for 0.4 pi less than or equal to omega less than or equal to pi. So see, if in the question, if they have given alpha s, alpha p, omega s, omega p, it is very easy for you for substituting those values in the given formula. But here you have to extract what is alpha s, what is alpha p, what is the value of omega s, and what is the value of omega p. If such questions are appearing in the examinations, you have to remember the or get back the magnitude response of the filter. See, in the previous lectures itself, I explained you the the basic magnitude response of the Butterworth low pass filter. Let me recall that. So this is the magnitude response of the Butterworth low pass filter. I explained you. So this is the higher order. See, the h of j omega is maximum here, 1 here, and here the first parameter specifying the allowable pass band is equal to 1 by 1 plus epsilon square, and this is the 1 by root is the 3 dB frequency I have taken, and here the maximum allowable frequency in the stop band I am indicating is a 1 by 1 plus lambda square when the 0 is when the omega is rolling from 0 to omega. So from here to here, if you calculate, so this is the first frequency you can encounter is the omega p, because this is the pass band, and here you are going to stop band. So here if you see, this is the omega s is the stop band, and in between these two, what at the 3 dB frequency, whatever the frequency you will get is the omega c. See, that's why I told you the magnitude response, reading the graph of or you can say the reading the magnitude response of the filter is important, because sometimes they may ask you, they may give you only the data. They may not give you only the data, they may give you the conditions. Now let us draw the response of the filter now for the current problem. See here, he said h of j omega is in between 0.9 and 1. So 0.9 and 1, the h of j omega is here. Okay. When the omega when the omega is ranging from 0 to 0.2 pi. So here I'm ranging the 0 to 0.2 pi. The omega is in between 0 to the h of omega is lying between 0.9 and 1. So 0.9 may be the maximum allowable frequency. So it can be a 1 by 1 plus epsilon square. Now the same he has given the h of j omega value is the h of j omega value is less than 0.2. So if it is less than 0.2, then h of omega is omega value at 0.4 pi. So 0.4 pi. So 0.4 pi to 0.5 pi. So 0.4 pi. So this will be the 1 by 1 plus lambda square value. So now from here, now you can extract the data. So the first frequency will be the 0.2 pi will be the passband frequency, and this frequency 0.4 pi will be the stop band frequency, and this is the 1 by 1 plus epsilon square is equal to 0.4, and 1 by 1 plus lambda square is equal to 0.2. So this is the extracted data from the given specification. See, for solving such problems, here you know all the formulas only, but the data extraction is important. The data extraction is important. Now having these problems, you can easily calculate the transfer function. So you know how to do the transfer function. First step of designing the filter is calculating the order of the filter. N is equal to log of lambda by epsilon by log of omega s by omega p. So if you got a lambda and epsilon value in the previous, log of 4.898 by log of 4.84. Now in the previous, now from this we have calculated this n is equal to 3.34. So n is equal to 4. For n is equal to 4, the transfer function of the Butterworth polynomial, we have fixed Butterworth polynomial s square plus 0.7653s7s plus 1 into s square plus 1.8477s plus 1. Directly we have formula. But this is the equation for the normalized filter. But you have to scale the this transfer function of the required filter, required omega c. The omega c formula is omega p by 10 power 0.1 alpha p minus 1 of 1 by 2 power n. So omega p is the passband frequency which we already have. So 0.2 pi I have substituted, and this all together is called as e power 1 by epsilon power 1 by n. Epsilon power 1 by n we already calculated in the previous 0.484 by 1 whole power 1 by 4. So this is the value we got. So after substituting the h of s over 0.4 pi, substitute s is tending to s by 0.24 pi in h of s. So in this s of h of s, we have to substitute the each and every s value by s by omega c, because this is the actual transfer function. So this is the transfer function for we have assumed it as omega c is equal to 1. So you can say it as a normalized filter. But for this filter, for this we have to substitute s in place of s, we have to substitute s by 0.24 pi in the h of s. So in the above equation, wherever you see the s value, substitute s by 0.24 pi whole square. See, I think I told you why we have to substitute, because we are substituting it for denormalizing, because for the actual filter. So if you substitute this s square in place of s, if you substitute all these things, so the equation is turning into like this. So see, here the designing steps are important. The rest of the mathematical calculations depends upon how fast you are. So this is the equation you got at the entire. Okay, in such a problem, the key point is identifying the data exactly. Okay, thank you for watching my video.